Okay, this is Mr. Sitta. I've been working on the Chapter 5 review, Thermochemistry. Didn't get a good printing right here, but we'll go with it. I think it says a 30-gram sample of liquid water at 23 degrees is mixed with 29 grams of water at, it looks like 43 degrees. What's the temperature of the water? Final. I don't like this problem. Okay. And we said 30 grams. Boy, I hope that's right. It's going to look bad. I'm going to take this grams of water and put it into here. The heat's going to go from the higher into the lower, so this is your Q. This is 29 grams and this is 43, so this one is higher. So I'll just say this is number 1. I'll call this one number 2. So number 1, number 2. For number 1, you got Q equals Cp times mass times delta T. For number 2, you got Q equals Cp times the mass times the delta T. Okay. In this case, I actually have to pay attention to my sign, and because I'm asking to solve for the final, I have to know that delta T equals T final minus T initial. Okay. So what I'll do is I'll say the temperature 1 equals, the Q of 1 equals the Q of the 2, but it's a negative. So I'm going to make one of these negative. Okay. And so what I can do, I could solve for the Q and then use substitution, plug it in, or I can use the transitive property, which I like to use. So what I'm going to just say is that Cp times the mass of 1 times Tf minus Ti equals Cp the other times the mass of the other times Tf minus Ti. Now, because I can't read these, I'm just going to take it to this step. The CP's cancel out, okay? And figuring if number 2 is the highest one, I would say that this one is times a negative. I will plug all my numbers in and then solve for T final. And remembering that this negative is going to make this one become negative Tf and plus Ti. And that's what I hate about the whole sign thing. And this one will equal mass 2, and mass 2 will be times Tf times Ti. And what you then do is you get all your Ti's to one side, you get your Tf's, to the left side, get your masses to the right side, and you'll just solve it algebraically. And that's all I got to say about number 24, which I couldn't really see. Maybe if I sound on a computer, I can bring it up and see what's actually supposed to be written there. Okay. This is just like a lab I used to do. Okay. The heated solution of a sodium hydroxide is 44, and I take 13.9 grams sample. Okay. What you want to do is find your amount of heat that's liberated by throwing 13.9 grams into it. So I start off with dimensional analysis. 13.9 grams of sodium hydroxide. You know, I'm not going to put a problem like this on the test, I'll tell you right now. That's not happening. Not in COVID-19. Okay. I want to know the amount of heat, the amount of kJs, which is going to be your Q. It's really not that hard though. Grams to moles, sodium hydroxide is 40.0 to 1 NaOH. And then for every mole I get 44.4 kJs. And this heat is going to be released. So I'll tell you in the big picture, the temperature of this is going up. Whatever solution is, it's increasing because it's exothermic. I'm not really getting into the signs. I'm not going to put a negative there. I could. So let's see what we got. 13.9 divided by 40 times 44.4. I get 15.4 kJs, and that's my Q. And I guess after this I'll start thinking about sign. Okay, maybe not. Okay, I like this because this combines dimensional analysis, and then the problem is asking for a final temperature. Well, the final part of this problem is you need to find Q equals Cp times mass times delta T. So, you know what? I'll do it without thinking about signs. I know the temperature's going up, okay? I'm going to solve, to get the final temperature, I'm just simply going to algebraically rearrange and solve for delta T. Well, it's equal to Q divided by Cp divided by mass. And this Q has to be in joules, so I got a problem. I got to take these kJs and convert kJs to joules, so I got to multiply it by 1,000. So in Q, this is 15,400 joules. And that's where many of the people will get this problem wrong, is they're not thinking about signs. They're not thinking about units. So what I got is 15,400 joules. The Cp of water we're going to use, 4.184. Usually when you have a solution, you just consider it that it's mainly water, so they use 4.184. And then the mass, well, the mass is the fact that we added the 13.9 grams of solute, we added it to 250 of water. So the mass turns into 263.9 grams. There's another part where you can screw this up. Okay, you got to have the mass of the solution, which is solute, NaOH, plus water, solvent. That makes the solution. Okay, so here we go. 15,400 divided by 4.184 divided by 263, and I get 14.0 degrees Celsius. Now the initial temperature was 23. I know this temperature is going up because I know it's exothermic, because it's got a negative delta H, so I don't have to go all sign crazy. My answer should be 37 degrees is temperature final. So say I want to go temperature crazy, I could put a negative in here, put a negative in there, and I know my temperature sign is negative. Well, the equation for delta T is T final minus T initial. And I put a negative in there, negative 14. To solve for T final, I would add I would rearrange this, and I would add T initial plus T delta T, so it comes out to 37 either way. So I wouldn't go crazy with that. All right. Another one I don't like, don't care for this. This is too blah. I didn't make this. 100 milliliters plus 100 milliliters. Okay. They're both 0.3 molar. Both solutions are at 35, and the temperature was recorded as 37. Resulting was 37. So I know the delta T. What am I asking you to find here? I want to find the delta H of reaction. So this is kind of like the lab. This is HCl over here. This is NaOH over here. Okay, so we dump the NaOH in the HCl, and lo and behold, heat goes from one into the other. Okay, it went up, it's exothermic. So what do we got? We know that temperature is 35, 37 the final, minus 35. So the temperature change is 2 degrees Celsius. Okay. We know this is 100 milliliters. This is 100 milliliters. So a milliliter equals a gram, so it's 100 plus 100, so it's 200 grams. That's my mass of the solution. So now I'm going to fly into Q equals Cp times M times delta T. So I know that I'm going to assume it's mainly water, 4.184 joules per gram degree Celsius. The mass is 200, that's the total. And the delta temperature is 2 degrees. And degrees Celsius cancels. So I got 4.184 times 200 times 2. I got 1672 joules. And that's a Q. And I'll say that Q, let's make it negative because the temperature went up. So to find delta H, I want to turn this into kJ, so I'm going to divide it by 1,000 joules per 1 kJ. So delta H is negative Q divided by the moles. So it's negative 1672, 1.6 since I just divided by 1,000. Now it's kJs. Now how do I find the moles? Well, I have 100 milliliters. Find some room to work. 100 milliliters times 1,000 milliliters to 1 liter times liters to moles, and that's 0.3. So it looks to me like 0.03 moles. So I'm going to divide that by 0.03 moles. And I got 55.7A, negative. Negative 55.7. I actually think that's close to what I did on the lab. Okay, I'd rather do that one. These are all kind of lab questions. MgO reacts with water to form MgO if 5 grams is combined with 100 grams. Look at your interactive lab if you want to see problems like this. The temperature, the resulting went from 22.3 to 39, so I got 32.9 final minus 22.3. 10.6, and that's my delta T. T final minus T initial. Okay, the mass is going to be 5 grams plus 100. Solute plus solvent, so you end up with 105 grams of solution. So we go into Q equals Cp times M times delta T, because I got a temperature job and changed. 4.184. I know since I got a temp change that I'm using this equation, and I want to find the Q because they're asking you to find the delta H. And the delta H is going to be negative Q divided by moles of magnesium oxide. Okay? And so I got times 105, grams cancels. And I got delta T, which is 10.6 degrees Celsius, cancels. And what do I got for Q? 4.184. That's a 4. Times 10.6 times 105. Q is equal to 46,057 joules. Convert joules to kJs. Divided by 1,000. 4.657 kJs. Now, the water gained this, so this was positive to the water, but it's negative to the reaction. So this is going to become negative 4.565. 7 kJs. Okay, divided by, now I need to find the moles of magnesium. So 5.0 grams. Gram to mole of magnesium, 24.3 plus 16, 40.3. that times 5.124. That's your moles of magnesium. Now, here's the thing. To find moles, I can't deal. This 105 is water and magnesium. I just have to look at the 5 grams of magnesium, and the water did not produce any of the heat. So this is 0.124. So make sure you're not including the total mass of the solution. You just want the 5 grams that you put in there. Okay, times 4.657. I got 37.5, and it's negative since it's exothermic. That's the way I tend to think of these things. The temperature went up, it's exothermic, so I know it's going to be negative, and it's going to be A. Bingo. Okay. Hess's law, thanks goodness. Let's just roll these out. Okay. I know this delta H. I know this reaction. Well, I multiplied everything by 2. Very easy. You multiply this by 2. So it's looking to me like negative 967 B. Just on the fact that you doubled it. Okay. Find the enthalpy change for this, that, and that, and that from that. I kind of rearranged these when I reprinted them. You'll find out I gave you hints and rearranged them. This is Hess's law. So what do I have to do these two to get to this 2? Well, the F2O3 is on the left-hand side, so I have to reverse this one. They did not give me enough room to write here. That doesn't make me happy. So I'm going to switch this to 2Fe plus 3/2 O2. Now it's on the right side. Well, what I do is I turn that into a positive. Okay, but I need a coefficient of 2. So I need to multiply everything in here by 2. 2, 4, and then just 3. So I have to multiply my delta H by 2. So I end up with 2 times 824.2. I end up with positive 1648.4 kJs. Okay, let's look at the rest of it. Carbon is on the left-hand side, so this is correct as far as its sign. But I need 3 carbons, so I'm going to multiply everything in this line by 3. So I get 3, 3, 3. Okay. Let's see. I need to multiply the delta H by 3. So 3 times 393.5. That's negative 1180. I can get my answer right now. Just add them up. And should be a positive 467.9 kJs. Okay, if I go back to this, the 3O2 CO2, I'm missing something. Oh yeah, that's present in the final reaction, so it didn't cancel. The 4Fe is present there. The O2 ends up canceling. So the 3O2s here cancel with these, so you don't see any O2 in your final reaction. And you got 3 carbons and 2 F2s, so everything's good. Okay, find this reaction from these two. Again, I'm not getting a great amount of room to work here, so it doesn't make me happy. 2E is there. So this one checks out. Don't have to do anything to it. O2, I'm going to leave it alone. Got it there, got it there. You know, I can predict, since it's on the left here, and I need a 3, this is going to end up being a doubled. But I'm going to use the EO3 to find that. EO3 is only here and it's doubled, so that means I got to double everything there. There's your oxygen doubling. Doubling. Okay. The 2 EOs cancel out. I got 2 E's. 1 plus 2 makes 3 oxygens, and 2 EO3s is my final. Everything else canceled out. I did double this one, so I had to double this one. So negative 392, I think. And I'm going to then, Hess's law, add these up, Hess's law summation, plus 333. I get negative 725 kJs. D. Rolling right along. For the ethylene below, I give you the delta H. What's the value of H if the combustion is treated to liquid water rather than water vapor? Okay, that sounds really tricky. Well, basically, they don't give you the final reaction. I want to turn this gas into liquid. And now we're missing a sign here. So the final reaction I want to get is C2H4 gas plus 3O2 producing 2CO2 gas. And we want to produce 2 H2O liquids and find out what's the delta H of that. Alright, so I'd say they're trying to make it tricky. Okay. This is water going from a gas to a liquid. So I want to get 2 of these, so I'm going to multiply this equation by 2. So 2 here, 2 there. What happens? The gas cancels out. The water becomes your product. So I need to take this delta H and multiply it by 2. So what I get is I get negative 88 kJs. Sum it up. So the answer is negative 88 plus negative 1323. 1411. Negative. E. Didn't really like the problem. I don't like this one at all. I mean, come on, give me numbers. X, Y, and Z. Alright, I'm trying to get this equation. They're not really nicely lined up, nor does it give me a lot of room to work, so I'm not happy. N2O2 is right there, so basically I need to flip this reaction. Well, since I don't have any room, I got to write it up there. That really gets me happy. Okay, 2Na plus 1/2 O2. That means this becomes a negative Y. Okay. Oxygen ends up canceling out at the end. It's not even there anyway. I'm looking for the liquid water. The liquid water is on the wrong side, so okay, I got to flip this one. So X is going to be a negative X. Okay, I don't really have, running out of room to flip things. H2O liquid going to H2 plus 1/2 O2. Okay, and then the last one, NO, thank goodness I don't have to flip it, but I do have to multiply everything by 2. 2, this becomes a 1, this becomes a 1, and this becomes a 2, and I need a double Z, so this becomes 2Z. My answer is right here. The delta H is 2Z minus Y minus X. 2Z minus X minus Y. That'll work. Looks like D. I didn't like that one. What canceled out? Basically everything that should cancel out. 1/2 oxygen plus 1/2 oxygen makes 1. And that